How you guys doing? So we're going to do some more assembly today, as you probably expected. I don't have slides for what we're doing today, so you just have to either have a perfect memory or take really good notes. And I'm not even sure I'm going to have, that might be sort of the trend from now on, is just for me to sort of just present material as it comes to me. So the first thing we're going to do is explore register operations and try to relate that to the flags register. Okay? I've got the flags register up over here. So I'm going to be switching back and forth so you can see what's going on there. First thing, we'll break into data center. Did you guys install FASM on your computers? No, excellent. I'm proud of you. Okay, so now we're going to start with. We should do that. And we talked last week about that move did not affect the registers. Did we talk about that? Okay, so in order to verify that, what I want to do is show you now in Visual Studio how to look at the registers and verify what's happening according to the operations that we're doing. So first, I'm going to. Do you see the little red dot there? That's a breakpoint. And in Visual Studio, to set a breakpoint, you just hit F9. Okay. And then when you debug Visual Studio, you're going to stop at that breakpoint. So in Visual Studio, the debug key is F5. So if I hit F5 right now, it's going to stop on that breakpoint. Okay? So, very important, just make sure you realize to set a breakpoint F9 to run in the debugger F5. Now notice that we have all these registers up here. Okay? And in order for you to show those in Visual Studio, you just go to Debug, Windows, and way down here, there's a register selection, okay? I know there's a shortcut keyboard shortcut, but I never remember it. Now just take a look at these registers. And the first four should look extremely familiar. EAX, EBX, ECX, EDX. We talked about those a bit. ESI and EDI, we talked about those as the registers that we use to access data in specialized ways. This is the instruction pointer, ESP. No, just kidding. You know, ESP, get it. Twilight Zone, whatever. Stack pointer, right? EBP is the base pointer, which we'll end up using today. And EFL, what do you think EFL is? The flags register, okay? So take a look at what you got right there. 204, you guys are brilliant, right? If we were to convert 204, that's going to be a hex number. If we were going to convert that to binary, what would it be? I have a freaking whiteboard in this classroom. What would it be? Let's see, it'd be 0, 0, 1. Wait, 0, 0, 1 for sure, right? Now let's go back and look at our flags register. 0, 0, 1. Is the carry flag set in that example? No, because it's 0, right? Okay, is the undefined flag set? That's a joke. But the parity flag was set, wasn't it? Let me go back. In order to evaluate which flags are set, you have to convert this to binary. Okay? 4 is 0, 0, 1, correct? And let's see, the next two, we're actually only going to use the bottom 8 bits anyway, so it won't really matter. The overflow bit is acceptable. We'll ignore that for right now. So all you need to do is convert those to this. So the only flag that we're interested in right now that's set is that 4-bit. That's 0, 0, 1, right? And as I said, that's the parity flag. We're not even going to worry about that today. Now, let's go ahead and execute. And by the way, in Visual Studio, to execute a single step is F10. So if I hit F10, it will just single step over that. Okay. Now, did it affect? Well, it did other things. What is that converted to binary? 6 in binary is 0, 1, 1, right? Okay, and that 1 bit is unused, so we're going to ignore that for right now. Okay. Really, for today, the only bits we're going to look at are going to be the carry flag and the 0 flag and the sign flag. Okay. So bit 1 and bit 6 and 7 are the only ones we're going to look at for today. Well, excuse me, bit 0, you're right. Bit 0, carry flag. Yeah, bit 6, 0 flag, and bit 7, the sign flag. Those are the only ones we're going to look at for today. Although the other flags are important, but not for our usage. And eventually we're going to look at the overflow flag, but not today. Okay, so that'll just kind of keep it more manageable. Okay, so now we're done with our program. It's finished executing. Now let's see if we can do something that might affect the flags. Let's add. I shouldn't do that. I say that every time. Visual Studio can be really stupid. Let's add 44. Let's see if that. And I'm going to put just an extra instruction here, just so it doesn't. Okay. So you remember what I told you to debug it was F5. And every time you make a change, it's going to recompile before you run it. Do you guys use Visual Studio in Intro to C at all? No. Great. F10, step over. Okay. Now let's take a really close look at the flags here. We're just adding to EAX. Nothing happened, right? Why wouldn't anything happen? Well, did we have a carry event? Did we have a sign event? And did we have an overflow event? None of that stuff happened, okay? So that's why we didn't, our sign flag didn't change at all. Okay, so let's see if we can change that up a little. Let's do a subtraction. Instead of subtracting 44, let's subtract 144 and see if that changes it. So predict, what do you think is going to happen? When we do the subtraction, what do you think? Okay, take a look at the flags. Before we do this, take a look at the flag register. Ooh, something changed, right? Value there is 83, right? 83. So let's see if we can relate that to the flags. What do you think happened? No, we actually, damn. I wish. Okay, so bit 7 is set. Okay. So real geeks have these things memorized. So bit 7 is set. What does that mean? That's the sign flag, right? Does that make sense? That the sign flag got set. Let's see. It was 83. Carry flag is set, and so carry flag is also set. Okay. Now, do you remember those? Do you remember those conditional jumps? What were those conditional jumps we looked at? I know you don't have them memorized. We just glossed over them, but they were jump of Z, that means jump of 0, jump of carry, JC, jump of less than. Remember, we just did one of those. But one of them is called JC, jump and carry. So if I do a subtract, then I could do an operation like jump and carry. And what I'm trying to do is get you to understand how these flags affect how your programming can go. So what we're going to do is set a couple labels here. Label 1. This works in Visual Studio like it's supposed to. Label 2. Now we're going to do a jump if carry. Label 2. And then we'll do an unconditional jump to label 1. Oh, we don't need to. Let's put label 3 out here. Just do an unconditional jump to label 3. Label 2, let's go ahead and set EX to something. And G, thank you so much for that. Crap, that really needs to not do it. Okay. So now let's kind of run through this. And as we run through it step by step, we'll try to see if we can predict what's going to happen. Okay. So we already said that this isn't going to affect the flags register, although it might affect that unused flag. Okay, F10. Now this is definitely going to set the carry bit, correct? You see the carry bit set. So what predict? Where should it go? Where should it jump to label 2 or not? It should jump to label 2 because the carry bit in the flags register is set. Okay? And sure enough, it jumped to label 2. Now let's change that value to subtract. Instead of 144, let's subtract 44. Okay? Now how will that affect what happens? Well, is the carry bit set? Carry bit is 1. Okay, yeah.
I'm a little confused as far as like I see versus EFL. That number is represented as a hex or a decimal.
That's represented as hex, and that's one of the problems we're having right now. And I'm just trying to.
So it's like hex to binary. So I'm tracking now. And then
Yeah.
And then we're okay.
And that just makes it sort of hard to do the conversion. There might actually even be a way to even display that. There probably is. Visual Studio will probably actually display that as a binary. Pretty sure it will do that. I think you have a choice on doing that. I forget how to do it though, but I've done it before. Yeah, right. Show us. Okay, so now it's not the ship jump.
That's where I'm at. We're used to it. Convert, check.
Yeah. And the carry flag is actually bit 1. So if EFL has in the rightmost digit, it has an odd number, then it's going to be that bit would be set. The carry flag. Okay. So now it just does this unconditional jump to that thing we had set. Okay. Any questions so far on carry, not carry, and so what have we been using to trigger that carry flag? A subtraction that was bigger. When we subtracted a number that was bigger than the register, right? And what didn't trigger that carry flag? When we subtracted a number that was smaller, right? Pardon me? Okay. Now what happens when you subtract the exact same number? Man, send you to college. All right, so let's go ahead and run it now. This is the exact same value now. And by the way, before we go there, let's just check. What's our 0 flag? Our 0 flag is going to have the value. There's this first digit and then the next digit. In the second digit, the hex value should be 4, or yeah, should be 4. So let's see what happens here. Now let's check. As predicted, the 0 bit was set, right? The 0 flag was set, and we said have value of 4 in that, that's actually called a nibble. It's 4 bits. Okay, so how would we do this here? The carry bit has no, the carry bit doesn't interest us at this point, right? But there's a special jump called jump if 0. Okay, and here again, I gave the table of jumps, and at a certain point we'll do like an exhaustive treatment of all these jumps that we're going to be using. But for right now, let's just go with this 0. So now let's see, and see if we can predict what's going to happen as we step through this. Okay. So now, when we subtract 99 from 99, the 0 bit should be set. And this should jump conditionally to label 2. And it does. Let's try it when the 0 bit is not set. Let's subtract just one less. Let's only subtract 98. Okay. Will it jump here or not? Will it jump to label 2? No. But it unconditionally jumps to label 3. Okay. Now, that was kind of a setup for some of the math we're going to do here. So, I didn't do this set of slides. I have all the math. Oh, by the way, here this is on the web course, so you need to make sure you pull this down. I don't know if last week we talked about the math operations. For add, and I was looking for multiply. Now, let's go back and get the slides. Okay. So now let's do some multiplication here. Let's move on. When we multiply some smaller numbers, just to make it clear what we're doing. So put 5 there. Ax 7. Okay. Now, pay attention to the DX register. So nothing happened in DX, right? And AX, that's the hex representation. Okay. Did it set any of the flags? No. Now let's do a div. Oh, I see. Okay. Okay, so there we move 30 is and that's a hex. The EAX is hex. The EEX is hex. Okay, so let's do the division. And what do we get? Good number. Okay. now let us, two more math operations we're going to do. Inc, not really math, EAX, predict what will that do? What do you think INC stands for? Right. So let's see what happens. And okay, here it is. And it didn't affect any flags. So increment doesn't affect any flags. What do you think the flip side of increment is? Increment. Yep. And this also won't say flags. That's actually only half truth. At this moment, it won't say flags. So decrement the value. Okay? With me? Okay, so what I'm going to do is write up an assignment based on the add, subtract, multiply, divide stuff for web courses. And I will go ahead and upload it, say, Friday afternoon. So what you'll need to do is to make sure that you have Visual Studio installed and you can do this. And I think for Macintosh, you can still install Visual Studio, can't you? Mac people? Can't you run Visual Studio on Mac? You're saying yes. I have students in other classes. I don't have a Mac. Well, I do, but it's not a laptop. Okay. So I'll put an assignment on web courses for this. And let's go to one more thing that we did earlier. Shift right EAX, 1. What do you think? What's it going to do? Now we had this before. We had this when we talked about, remember when we were doing binary operations, what do you think shift right is going to do to that value? Okay, remember, visualize your bits, right? 30 would be what? Would be 8, let's see, it'd be 16, and an 8, and a 4 and a 2, right? If you shifted those right, what would happen to the value of 30? It decreased. You're dividing by 2, remember? When you shift right, you divide by 2. Okay, so let's go ahead and run this. And what value should we see in EAX? We should see 15, right? So here we load it. Now watch the EAX register, right? Puts the EAX values. So there it goes to 15. Shift it right. And which is going to be faster for the processor to do, you think? A shift right or a divide by 2? Shift right is really fast. Now, these registers also will allow you to shift more than one bit or one place. So I could actually shift 3 places. How much would I lose then? What would the value then be predict? It's 30. Are you dividing by 3? Or 2? Or 4? You're closer. 8 is a power of 2, right? So, and this is doing integer math, so it'd be 30 divided by 8 using integer math, so you're going to lose some value, correct? I mean, there's no way you can avoid that. You're going to lose a little bit of value just because you're doing integer math. There's your 30, divided by 8 is 3. And here again, it's not accurate because when you do integer math, you always lose precision. So, what would happen if I did this? What would that do? Multiply by 8, right? So we should get 240. Of course, it'll be in hex. That's 240 hex. That's correct. Okay, so these math operations are fairly easy and fairly straightforward. So what you're responsible for this assignment this weekend is move operations. I think you can do that, right? And we're moving to EAX. How big was EAX? 32. How big is AX? 8. 16, right? AL is 8. AH is 8, right? What are the other three of those general purpose registers? You have EAX, EDX, ECX, EDX, right? And they're all the same as far as that goes. Okay, I'm going to show you one more thing before we move on. We're going to use that, the FASM disassembler. There's a special thing with C, ECX, that's similar to a for loop. If I say move ECX, comma 5, it's only 5 because I don't want to do this forever. Oh, I need a label here. Let me say a label 1. And you can name these labels wherever you want. It's just like variable naming rules. Okay? So, that's wrong. And I'll say loop ECX JNZ label 1. So this is just like a for loop counter in C. Essentially, you put the value you want to count to in ECX. And see, this is a special thing. None of the other registers do this, only ECX. Okay, and it just loops over and over and over again until the counter is done. So that's a very handy, very fast thing that they've given us. Okay. Now we talked a little bit about function calls. And we did it in Visual Studio. It's a little bit harder in Visual Studio because Visual Studio sort of does its own things as far as functions go. So now I'm using FASM. And first I want to point out that this is kind of the basic bones startup code. And you don't have to retype all this stuff up. If you look, there's a folder called examples, and there's one called hello. Just grab hello.asm, and that's what I did. I just grabbed it, and I edited it just a little bit because we don't want to use it as is. Notice that I put a source code comment in front of this invoke. And so you know how in C++, what are the C++ comments? It's C++ and Java is // but in C it's what? / asterisk, and then you end it with asterisk \, right? So in assembly, you start each line that you want to comment with a semicolon. And you thought semicolons were no good after C. Okay. So at the very least, your program has to call this exit process. Otherwise, the processor will go on and on and on into infinity. Who knows what it's going to hit? Probably end up formatting your hard drive. So in order to, you have two options. You compile it first. That's fine. Or you can run it, and if you run it and it needs to be compiled, it should compile it for you anyway. So you didn't see anything because it's blinked, right? And if you want to stick this thing in there just to prove you actually wrote a program, you can stick this up here. I just copied that. That's actually how the hello example works anyway. Run it, just comes up with this. And I could say, we love computers. Okay. So let me get rid of this real quick. So the first thing we're going to do is talk about functions and data. So data. So the naming conventions follow the C naming convention. conventions. How do you name C variables? What are the rules for C variables? You can't start with a number. You can start with like an underscore or a dash. Maybe start with a dash. An underscore actually sometimes works good. So you can alphanumeric, no blank spaces. You can put numbers in there if you want to, but you just can't start with, right? So labels and data types in assembly are the same thing. So just to show you, I can store just like variables, just like I do in C. I can say my value, and this is just my convention. I usually do a flush left. DD is a 32-bit value. I have to actually put a value there. You can either put an actual value or you can put a question mark. And the value means that's what it's going to be, 0 or 5 or 10 or whatever. Or question mark means it's undetermined, okay? And when you leave it undetermined, sometimes that's good because then the assembler can optimize your program just a little bit better. Your value. DW3. So what's the difference between DD and DW, do you think? DD is 32 bits. DW, the W stands for word, okay? And how big is a word? 16 bits. Okay? And what do you think the other value, the other type we're going to? Character. It's value. DB 74. Let's make sure this compiles. Okay. Now, suppose I said 274. I wonder if I would get an error. Why do you suppose I would get an error? Yeah, this is too big, right? I could do 274 up here. That's okay because it fits, right? Right, so I'm good there. Now, to access these from your assembly code, you can say like move EAX, my value. Let's just make sure it compiles. Okay, compiles. Let's try something else though. Let's sort of see where our limits are. Huh, what happened there? Right, see, I'm trying to move a 32-bit number into a 16-bit register, right? And the assembler picked up on it right away, so let's make it your value. Just to prove we can actually get this right. Now it should compile. Where is my value arranged?
So the placement of declared variables don't really matter.
So as long as the program doesn't execute through them, I usually put them at the end, but you can actually even put them at the beginning. A lot of times you can create like whole data set. Let's call it the data segment. Oh, what happened here? And that should be working fine. I wonder if there's, did I misspell or something? What happened here? That should work fine. I'm not really sure what it's complaining about, but complaining about something. So I'll have to resolve that and figure out what's going on with that line. So the question he asked was, do the values always have to go to the end here? And the answer is, they can really go wherever it's convenient for you. You could do that, create what's called a data segment. And we're not gonna do that right now, but see how that's dot code, then you'd have a dot data down here. Dot data, like that, we're not gonna do that, but so you can create a data segment. Okay. And I'm gonna do my very best, at least for right now, to avoid the whole idea of segments. We talked about on Monday that the whole segmentation thing is kind of a throwback, but it gets pretty complicated. So we'll skip it for right now unless we have time. And then another way you could actually do it, and I've done this before, is you could just say real code. So you can put a label here and do an unconditional jump. Okay, you got it. Oh, the read code. Yeah. And then you could put all your data here. Because it would be okay, because you're not like, this won't compile because I've had to. It's just like in C if you have duplicate. I could put twos there. These things, but I still compile. So it should compile. Okay. So it's really kind of up to you. And I'll tell you something. I once had a program that I wrote for a very shady company, and I didn't trust them at all because I'd seen what they did. You know how strings, we talk about strings in C, they always end with a 0, right? You don't see it, but they always end with a 0. They're called null-terminated strings. And I'd seen some guy I knew turned in a program for this company. And he had in the very middle of the screen said test version, because he knew what they were going to do is not pay him to just use the program and ship it out. And so what they did was they took a disk editor and they went in there and they edited the string in the data segment. So it said, so they just nulled out the very first character and never printed it. So I got smart and I thought, okay, well I'll put my string in the code segment and you'll never find it there. Then I encrypted it within the code segment. So there are actual times when you want to do that. Especially if you're trying to defeat hackers from cracking your program, the first place they're looking is in the code segment, in maybe in Max, in the resource fork or something like that. So a lot of times they'll put stuff in the code segment to just totally throw you off. So you're not really expecting to see it there. So good question. All right. So that's how you can use, it's just like a variable in C++, or at least a reasonable facsimile of a variable in C++. Okay? Now, the next thing we're going to talk about are functions. So, function 1. So the very simplest function I could possibly have is do something here that is useful, and then just return. Okay? So if I come up here and I call function 1, it will call function 1. When it hits the call, it says, oh, call function 1, goes down, does everything in function 1, and then returns, and then execution resumes here. And what happens is the processor, how does the ret know where to go back to? The processor actually pushes the instruction pointer onto the stack before it makes the call. You don't see that, it's not something you have to do. So before it makes the call, it pushes the instruction pointer on the stack, jumps to the address, and then the ret pops the instruction pointer and goes back. That's actually not a very useful function, but I could possibly use it if I had to. So let's say let's call it multiply two numbers. Say multiply. Okay, let's make this call multiply. Okay? So I'm going to call multiply, but what is multiply? How does it know what to multiply? We have to pass it something. So I'm going to give you a few different ways to pass it something. First, I'm going to show you the very easiest and most basic ways. And frankly, the least useful, because the easy stuff isn't always necessarily useful. Move EAX, comma 5, move EBX, comma 6. Okay, that's not very useful. And I'll explain why in just a minute. So what we'll do is we'll just multiply EAX by EBX. Easy, right? Now, why is that not very useful? And by the way, the return values we talked about last week, they're always in EAX, so that's already fine. EAX is why is this not very useful? Yeah. What if EAX and EBX are being used for something somewhere else, right? What if now I've just hosed up my whole use of EBX? Or what if I have 15 things to pass, 15 parameters to pass, or whatever? So this has the sort of a usefulness, and the biggest advantage of doing something like this is it's really, really fast. This is the fastest way you can possibly call a function. Okay? So if you can get away with it, do this. Okay? But you may not be able to get away with it. This is the very fastest way to call a function. Really, that's a very unrealistic way to do things. So now, we're going to give you a C++ equivalent of multiply. So you can kind of relate this to what you're doing, okay? Because I know you've all had, I say C++, but I really mean C, it's the same thing. Well, that's either one, but it's similar, at least, right? Void. Multiply int first, int second, right? And that's a function you all can understand very easily, right? So what we're going to do here is we're going to push, what's that value, 5. We're going to push the value of 6 onto the stack, okay? And if we push 5 and we push 6 and they're on the stack and we call the other guy, then he should be able to yank those off the stack and use them, right? Okay. The problem is when we push those 2 on the stack right here, we messed up the stack pointer. So right here, when we resume our business, we gotta restore the stack pointer toward where it was, okay? You follow that? If we push onto the stack, the first value was 5, the second value was 6. We're pushing 32-bit numbers. You got to make sure that when you're done, you clean up the stack pointer and you put it back to where it was. Otherwise, your whole program gets like all messed up. Okay.
So why is it 8?
It's 8 because each of these are the 32-bit values. A 32-bit value is 8 plus 4 bits. 4 bytes. So 4 bytes times 2 is 8 bytes. So if you push more, that would be a different number, right? What if you pushed 375? 12, right? Now, just for the sake of argument, if you're actually pushing registers, and you push like AX, how much? EAX counts for 4 bytes, right? How many bytes does AX count for? 2, that's very good. So you always got to remember what you're doing there. And only adjust the stack according to what you did. Now this part is very cool. We got it here. This part is not. Because he doesn't know how to pull, he doesn't know how to get stuff off the stack at the moment. So we're going to adjust the stack pointer right now. First, we need the base pointer, because that's how we're going to get this stuff off the stack, right? Right. But we're going to actually use the base pointer to address the stack. So we put the stack pointer into BP. Okay. Actually, we have to push BP and save it. So here we're going to push BP, because BP might, someone else might be counting on BP. Okay, so we can't just alter these registers and not put them back. So we push BP, and now we got to pop BP, right? We'll stop it and sort of analyze what we just did. First, we saved BPs just in case someone else was counting on it. Someone else might have set its values, and if they called our function and it hosted up their value of BP, then all of a sudden their stuff doesn't work, right? Okay. We move SP into BP so that we can use BP to address all those values that we push on the stack. Okay. And finally, before we leave, we pop BP so we can restore it. Now, the rule of thumb is parameters that are passed. So let's grab the first one. Move EAX BP plus 8. That's the first parameter plus 8. The other stuff below 8 is like the instruction pointer, and we've already pushed BP. Okay, so that accounts for that accounts for 0 through 7. That when we call the method, it already pushed the instruction pointer, and then we did something. We pushed BP. That's another 4. Okay. Okay. So actually, this should be ESP. Sorry. Okay. And so that's the first parameter. The second parameter predicts EBX, comma, BP plus, guess. They're each 4 bytes, right? 8 plus 4 is 12, so it's going to be plus 12. Now you got the second one, right? Now you do an IMUL, and the result's already going to be an EAX. And we said our return value was always going to be EAX, right? Now what's the one thing you can see that might be wrong with this function? What if someone was counting on the value of EBX? We just hosed it up, right? So what should we do to make sure that we restore EBX and then put it back again? We should push it on the stack, right here. And then pop it when we're done. I really hate this editor. I know it's not nice to hate. You with me? Okay, actually, this is what we're trying to do. Okay. Yes?
As far as what's this EBX, see, you have EBP plus 8, but you only have EP, is it supposed to be EBT as well, or is it supposed to be EBP as well?
Yeah, it should be EBP. Thank you. You say this certain embarrassment with this one. Thank you very much. Okay, now. Now, so what's the other thing about C programming that we're kind of missing? C functions have also what? Here we have parameters that we're passing, right? Sometimes C programs have what? Local variables, right? Okay, so there's going to have to come a time where we have to make some sort of allowance for local variables, right? So let me go up here and flesh out my C code. I'm not going to do that, but yeah, let's just write the whole C. Since I love this editor so much, it's just. So let's go ahead and so we don't really have to do this, but we're going to A equals first. B equals seconds. Return A times B. I know that's way more complicated than it needs to be. The comments here. So how would I declare A and B inside of my assembly function? Okay, the first thing I have to do is I have to give myself room on the stack. And I have to adjust the stack pointer. Okay. How much space do I need for A and B? How many bytes? So they're each integers. Each integer is 4 bytes, so I need 8 bytes, right? So I'm going to subtract from ESP 8 bytes. You understand the reasoning for that? Because I need 2 integer variables for a total of 8 bytes, right? Well, one small detail I've got to worry about here is I've got to restore the stack pointer. Okay? So right here, I'm gonna restore the stack pointer, ESP, EBP. Because now I've messed up the stack pointer. I gotta restore it again. So now, let's go ahead and move them into our local variables. Move BP. Now instead of plus was the direction we got stuff from. Our local variables are going to be minus. Minus 4 EAX. No, it's E. He's going to bust me on this one. It's EBP, right? I heard you. Move EBP minus what for the next one? Minus 8, right? Because they're each 4 bytes. Okay. So you see how we can do the same stuff that we did in C, as long as we know what the equivalents are. You guys are all very good C programmers.